last lecture we have talked about the types of the organizations. So continuing on that, now we comes to single accumulator organization. Actually, this type of CPU organization was used in back, where the CPU was much more simpler and the computers were in the evolving phase of their designs. So in single accumulator organizations, we have very less number of CPU registers, and as we have talked earlier, the bus is connected with ALU and a register known as accumulator AC is connected with ALU, and the output of accumulator is connected to ALU in this fashion, and here is the memory of computer. So this is basically the organization of a single accumulator, in which the accumulator register, which can store the results produced by the ALU, and the ALU can take, as well as the ALU can take inputs from accumulator also. So in this particular organization, the instructions can be zero address instructions, as we talked earlier about the zero address instructions, means the instruction doesn't have any address at all, or this design can follow one address instruction also. For example, instructions like INCA, we talked about this instruction earlier in our previous video. So basically this is an implied mode of instruction. I have talked in addressing that actually it is an implicit type of instruction, INCA. It means that it is implicit. We need not to give instructions to CPU that some data is to be fetched. Already the data which is to be incremented is in the accumulator. Actually the instruction is increment accumulator. So increment accumulator means AC will be incremented. If we write the register transfer language, then the register transfer language, the statement looks like this. This instruction doesn't need any operand at all. So this is basically zero address instruction. So this type of design, which is a single accumulator organization design, can have zero address instructions, and instructions like this, add X. So in this instruction, we can see that one address is given. The operation is addition, and only one address is given. So this is an operand. But we know that for the addition, we need two different operands. But we are given with the one operand only. Then what does it mean? We can, if this instruction is in the single accumulator organization, then definitely the content of X will be added with the accumulator. So the instructions will look like this. AC will be AC plus X. The content of X will be added with the contents of accumulator, and then the addition, then the output of the ALU will again shifted to the accumulator. So this is a one address instruction. So if we are writing one address instructions, definitely instructions will follow one another. Suppose we want to write add X. suppose we want to add x plus y, then in single accumulator organization we have to write code like this. Load x means the content of x will be loaded on accumulator. This will mean AC will be, x will be transferred to AC. Again, if we write like this, add y, then what does it mean? AC will be added with the AC plus y. So we can see by two single address instructions we can add x and y. If we can write this x plus y in a double two address instruction like add x and y. But if we write this particular instruction, which is a two address instruction, in a single address instruction, then definitely we have to write one and two instructions to add x, content of x and y. So single accumulator organization, we are having very less number of registers, due to which the instructions, the number of instructions will increase. The number of instructions will increase. This will lead to complexity. This will lead to the complexity for the programmer, because we have to write large number of codes for a simple operation. So these were the drawbacks. These were the basically drawbacks in the cost of less performing hardware. We can shift the complexity toward the programmer. So this was the problem with the single accumulator organization. These type of organizations were used in history. The computer was in evolving phase. So this is the design for a very basic computer. Now, so we can see that in single accumulator organization, we can have zero address instruction as well as one address instructions. Then we comes to general purpose organization. General purpose organization. General purpose organization. In this organization, we are having huge number of registers. We can have many registers. Suppose we are having registers named R1, R2, R3, R4, and many more like this. Rn. So this type of organization, in this type of organization, the instructions could be one address instruction. Oh, sorry, two address instructions, or three address instructions. For example, we can write add R1 plus, we can add, for example, the instruction is add R1, R2, means the content of register R1 and R2 are being added. And this can be written in RTL somehow. Content of R1 plus R2 will be transferred to R1. Again, this is basically a two address instruction. We can have three address instruction in this design also. So three address instructions will look like this. We are having enough number of registers, so we can use this design in such a way so that it will lead to the it will lead easy for the programmer, because the number of statements, the number of instructions will reduce. So this can be written as written somehow. Content of R2 plus R3 will be transferred to R1. So we can see we are having a fixed size for instruction, and if we increase the number of addresses in operand field, definitely this will occupy a large number of bits from the instruction format. So if we use large number of bits for the addresses of the operands, then definitely we are having one or two more fields for in this instruction. One is the operation code, and second one is the addressing mode. So if we increase the size of size of the operands, then definitely we have to compromise with the number of operations and addressing modes. So this will lead to the simplicity for the programmer, but complexity in the circuit design, because if we are having more addresses in our instruction, then definitely a more wide bus will be needed for the transfer of data, and as the number of registers will increase, the cost of the hardware will also increase. So general purpose organization is basically in which we are having enough number of registers to support 2 address instruction or 3 address instructions. Then one more type of the organization is the stack organization. So we will talk about the stack organization. So in the stack organization, actually the register or the memory is treated as stack organization. In stack organization, the memory of the registers are treated as a stack. Suppose these are the registers available in our CPU. So we can treat it as a stack. Suppose we in case of the stack architecture, we are having a pointer known as top of stack, TOS pointer, which points to the last element which is on the stack. So suppose we want to sum the content of 2 registers X and Y. What we will do, this stack organization will be having 2 basic operations. One is push, one is pop. As we have already seen these operations in our data structure, push means pushing the contents into the stack, and popping means the taking of the content from the stack. So if you want to add X and Y, then how the instructions will be written? What we will do, we will just simply push the content of X and push the content of Y and call the add operation. So when we suppose the top of the stack is here, and we run the push X, then definitely the content of X will be here, and again the top pointer will point to the next element, which is the top. Again when we will push, the content of Y will be here. The pointer will be shifted to Y. So content of X is in this block and content of Y in the next block. And when we call the add operation, the content of X and Y will be added and the result will be transferred to the top of the stack. Again the TOS will be pointing to this particular location. So in this way, with the help of the 2 operations, push and pop, we can arrange the registers or the memory locations in computer to behave like a stack, and with the help of the stack we can organize the registers or the memory in this fashion. So this type of organization basically supports 0 address instructions. We doesn't need any addresses to perform this type of operation. Only the pointer TOS will be pointing to the data, and when some operation, suppose add or subtract, will be called, the content from the 2 consecutive top locations of the stack will be operated with the operation, and the result will be pushed back on the top of the stack. So in this organization, we can have only 0 address instructions. So this was basically 3 different types of CPU organizations. Thank you.